Okay. It's okay. So I would like to begin, of course, by thanking the organizers, particularly Jorge and Modesto, for the kind opportunity to be here and be able to talk to you. It is always very nice to be surrounded by more Peruvian scientists and also potential collaborators. My name is Juan LOREDO. I'm a postdoctoral researcher in the CNRS, in the Center for Nanoscience and Nanotechnology in Paris-Sud. And today I'll tell you a bit of my work. I work in quantum photonics and the generation of non-classical light. So our center is located reasonably close from Paris. We're only 20K from here. And there I work in the group of Pascal Senelart. And actually, interestingly enough, in the group we are two Peruvians there. Omar Ortiz, who just gave a very nice talk, and myself. So what do we do over there? We work with quantum optics and artificial atoms. So we fabricate, we develop and study single photon sources based on solid-state technology. And our devices have evolved now to a point in which we can fit tens of these sources in a chip that is the size of a thumb. Why do we make them? What can we do with these devices? Well, we can explore optical quantum technologies. And we can do this because with these devices we can study very interesting properties of quantum physics, like, for example, superposition, which is the quality of objects in the quantum world to take upon different configurations, sort of simultaneously, and also entanglement, which is this property that deals with the correlations between the properties of different objects in a manner that goes beyond what can be explained by classical theories. So in order to find applications in quantum technologies, what you need, the resource that you need is, for one, single photons. And nowadays we live in a time where we can directly buy the sources, high-quality devices from, for example, Quandela is a spin-off of our group, and other companies as well around the world, like in Denmark. But another kind of resource that we need is, for example, photon pairs that are entangled in this quantum mechanical fashion, or states of light that have these so-called squid states that have a very reduced noise in one of the properties, like, for example, the amplitude. And now I will argue, and also, I'm just putting it already, I will argue that we are enabling a new resource for quantum technologies, and which is now we're able to create light that is simultaneously not only a single photon, but also two photons, and at the same time is vacuum, is no photon at all. So let's say you already have those resources. What can you do with states of light of this kind? Well, you can find applications for communication protocols. So you can have secure distribution of information in such a way that the security is guaranteed by the laws of quantum physics themselves. Or also you can find applications in enhanced precision measurements. Like, for example, we all heard of the detection of gravitational waves. This LIGO interferometer, they can use squeeze light in order to enhance the sensitivity of the interferometer to points beyond what would be possible otherwise. Increasing in the complexity, we can also work and build some so-called quantum simulators for simulating physics of very complex phenomena that actually, interestingly, doesn't even need to be physical. We can simulate non-physical scenarios. And the more complex of these applications is to, well, nowadays it's getting more popular, the word quantum computing, is to one day build a quantum computer based on light. So what I like to do now is briefly summarize my findings and the projects that I've been involved in these lines. So first, a couple of years ago, we were able to demonstrate the most efficient single photon source technology at the time. For immediately after, then we were studying the scalability prospects of these sources. And naturally, just after that, what we did is put this into practice and start scaling up the sources to eventually build multi-photon sources that can be applied in some quantum computing protocols. And very recently, and what I will describe very shortly as well, is now we are able to generate light in these quantum superpositions of photon numbers. Now, in the side of quantum simulation and computation protocols, we've studied from links between quantum entanglement and how is it related to geometric and topological aspects, to finding ways of efficiently computing quantities that are known to be very hard to deal with. And actually here in this paper, the Peruvian quota was a bit larger because for this paper, we collaborated with Enrique Solano. So some of you may know him. He's a theorist that has a group in Bilbao and Shanghai. And it was very interesting and very fun to be able to, I'm an experimentalist myself, to test the theoretical ideas of this project. All the way to projects for optimizing the weaknesses of entanglement, to protocols like boson sampling. For example, this protocol over here is the same protocol that maybe you have heard of recently, the claims of Google about this quantum supremacy experiment. So basically it's the same protocol, but of course in their experiment they've done it in a much larger scale, and this is the protocol version for photons. So now in the few minutes left, I will like to just give you a small description of how do we get light in photon-number superposition. I mentioned at the beginning that we work with artificial atoms, right? What we use is semiconductor quantum dots. And although they themselves are made of hundreds of thousands of atoms, they can behave all coherently like a single one because of properties like quantum confinement. Whenever an exciton is trapped in this material, it decays emitting just a single photon. So they are this artificial atom. And we know that if we have an atomic system and we resonantly drive the system, we can set the system in a genuine quantum superposition of being in its ground and its excited state. And then the natural question would be, what happens if, after you consider emission in the process? If the atom was in the excited state, then of course it will lead to a single photon. But if it was in the ground state, it will not emit any photons. So the question there is, if it's in a quantum superposition of being excited in a ground state, is the light emitted also a quantum superposition of a single photon and vacuum? And there is a lot of things I could say about this, but given the time constraints at the moment, all I can tell you is that the short answer is yes, that's exactly what happens. But not only that, also you're able to use these quantum emitters to produce a single photon and two photons. So if you are interested in more of these details, please ask me or maybe find more information on our work recently published a couple of months ago. But basically now with this, we are able to provide a new tool, a new resource for example, quantum information processes. We can do interference of many of these states. Now, what we can think of is, what do we do at this point? We can combine everything we've learned so far and combine it in a single, more complex unit, and for us to be able to increase on the complexity of the quantum information protocols that we implement. So, for example, we could imagine that all these lines, each of them is carrying a photon-number superposition state. Eventually, they can go into a photonic circuit like this. They can interfere, and from the interference and measurement of a scenario like this, we can perform some quantum computing protocol, for example. Now, maybe to just finalize, what I like to say here is that this is all nice, and I've been working outside Peru for some time now, but also what would be very interesting and maybe like some sort of a dream for us is, why don't we do this at home? We can do it. We know how to do it. Maybe the small big thing that is missing is more funding, right? But I hear in Peru is finally investing in these lines. So maybe, why not? Maybe one day we can do this either back in my alma mater, in the Catholic University, or many other universities where this could happen. So with that, I'll like to finish. I shouldn't forget thanking the Marie Curie scheme for funding my research. Thank you very much.